Good evening, students. Continuation of the previous lecture where we left, I started with that particular slide regarding the benefits of design of experiments in process optimization. So these are the 4 points which we have discussed in the last video. In continuation to that, we are going to see what are the conditions for selecting the design of experiments methods in terms of chemical engineering perspective. Okay, so design of experiments not only in chemical engineering perspective, I mean on all as perspective, I mean in general perspective with the chemical engineering examples. Okay, so factorial design condition to use when we need to go for a factorial design when studying the effect of two or more factors simultaneously. So the effect of variables simultaneously you want to go, then you just better you go for a factorial design. So one factor at a time, that is that means you are varying only one factor, not multiple factor. So here is a factorial design is a two factorial design or three factorial design. Okay, when studying the effect of two or more, then we need to go for a factorial design. When interaction between the factors are important, then we need to go for a factorial design. When full or fractional factorial approach is feasible. Okay, example. What are the examples for factorial design in terms of in chemical engineering examples? Optimization of catalyst reaction, temperature, pressure, and catalyst loading. The purpose to maximize the reaction yield and determine if there is any interaction between the temperature and catalyst efficiency. So whenever you want to find the interaction between the variables, then you go for a factorial design. So for this case, the factors which we are studying is temperature or pressure and catalyst loading. So maximize the reaction yield, determine if there is any interaction between the temperature and catalyst loading. Then factorial design is best. The second one, the factors are monomer ratio, initiator concentration and reaction time for process optimization to identify the condition for achieving the highest molecular weight and thermal stability. So the purpose is to find the highest molecular weight and thermal stability, that is a dependent or independent variable, this one for achieving. So this one is a dependent variable, that is a maximum we want to get it. That is like in the previous case we have talking about yield, right? So similarly in the polymerization process optimization, the dependent variable is highest molecular weight and thermal stability. So when you have achieved this one, optimize by varying the factors like monomer ratio, initiator concentration and reaction time. These are the independent variables. Okay, so these are highest molecular weight is a dependent variable, that is a maximum factor which we are looking for. In that case also we can go for a factorial design. When we need to go for a response surface methodology, when there is a non-linear relationship, underline the word non-linear relationship exist between the factors and the response. So let's say between the factors, what are the factors? Is a dependent variable. Independent variable, right? So the factors are that, let's say temperature, pressure is all independent variable. So the factor response is a output, that is a dependent variable. When there is a non-linear relationship between factors and the response, then we need to go for a non-linear relationship. Okay, when fine-tuning optimal process condition, okay, when a quadratic or higher order polynomial model is needed. So when you go for that case, then we need to go for a response surface methodology. The example in chemical engineering perspective, biodiesel production. Okay, methanol to oil ratio, catalyst concentration and reaction temperature. These are the independent variables. So what is the dependent variable? Maximum yield. Biodiesel yield is a dependent variable. So to maximize the dependent variable yield by developing a response surface model. Optimization of a batch fermentation process. The factors, that is a independent variable, or glucose concentration, pH and agitation speed. The purpose is to optimize the ethanol production using yeast fermentation. Okay, so the ethanol production is the dependent variable. Okay, with using yeast fermentation. So in that case, the relationship between the factors and the response, the variables, that is the independent variables and dependent variable is a non-linear relationship. Okay, in that case we need to go for a RSM. Hope you understood what I am trying to say. Okay, so next point is Taguchi method. When we need to use the Taguchi method, conditions should to use when minimizing the variability and improving the robustness. So variability. So how much variables? Reduce the number of experiments we have seen. Minimizing variability. Minimizing variability is not number of experiments. Variability is the number of variables which has been connected to the dependent variable. Okay, instead of 3 variables, 5 variables, because sometimes if you see, I could give a very good example, the differentiation, initial partial differentiation and differentiation, right? So the partial differentiation will talks about many factors, but only one factor, because in fixed first law, dou C by dou I, right? So dou Z. So the it's not with respect to distance, the change in concentration only is not a factor. There are other factors also. Predominantly, we are taking that one. Okay, so that's why we put dc, what you call dc by dz. Okay, so when you have why I'm trying to say is that we are not relating. I mean, there are multiple factors which may be involved for the response, but only which are significant and more effect on the response, that only we are taking. The other one we are neglecting it simply. Okay, hope you understood what I'm trying to say. So when minimizing the variability and improving the robustness, when experimental resources are limited, so resources are limited, number of experiments is come down, then we can go for a Taguchi method. Okay, when designing the experiments for quality improvement. Okay, so when you want to go for a quality improvement, then better you go for a Taguchi method. Minimizing the defect in injection molding. So try to reduce it because it's already in the process of production injection molding, but we want to reduce it. In that case, we can go for Taguchi method, mold temperature, cooling time, and injection pressure. The purpose is to achieve the uniform polymer part quality with minimal defect. So minimizing the defect, then we can go for a Taguchi method because that one is a design of experiment for quality improvement. The second part, optimization of electrochemical corrosion prevention. So when you want to go for corrosion prevention thing, then we can go for Taguchi method. The factors is electrolyte concentration, coating thickness, and voltage. These are the dependent variable or independent variable. Independent variable. So the purpose is to reduce the corrosion. That means to enhance the corrosion resistance. Okay. So if you do enhance the corrosion resistance, that means corrosion will not occur. That's the mean, right? So in that method, we can go for Taguchi method. And central composite design. So central composite design will give you a more number of experiments when compared to the box vehicle, right? That's what we have seen in the last lecture. We'll see what when we need to go for central composite design. Okay, when recurring a second order polynomial, even RSM also second order polynomial or second order. Okay, so what is second order? I will tell you actually in the coming few slides. Okay, when recurring a second order polynomial model for optimization, then we need to go for central composite design. There are, I just mentioned only few designs, the design methodology. There are other design methodologies like a D design. Okay, D optimal design is there that I did actually during my PhD. Okay, so it is similar to the central composite design only. Box Becker D design. What is the number of variables? Okay, how number of experiments? How what are the composite point? What are the points which has been taken in a what do you call it? Range, that all need to be studied. Okay, when recurring a second order polynomial model for optimization, when investigating both linear and quadratic effect. So linear and quadratic effect for both the case, then we need to go for central composite design because sometimes it may be linear at the lower range, maybe quadratic will have a higher range. So I want to find out both investigating the both linear and quadratic effect. Then we need to go for a central composite design. When a factorial design needs to be augmented with additional central and axial points. This is what I told you, right? So the points need to be identified. When a factorial design needs to be augmented with additional center and axial points, then we need to go for a central composite design. So the examples are optimization of heavy metal absorption in wastewater treatment. So the independent variables are pH, absorbent dosage, and the contact time to develop a optimized absorption model for metal removal. Okay, so heavy metal absorption is a surface phenomena. So we have absorption dosage. So in that case, we need to go for a central composite design. Supercritical fluid extraction. You know already what is supercritical fluid extraction. Is neither a gas nor a liquid, but it behaves like some properties behaves like a liquid, some properties physical chemical properties will behave like a gas. So in order to attain a supercritical fluid, you need to bring a condition stating that above the critical temperature, critical pressure and critical volume. So you know already what is critical temperature, critical pressure and critical volume. I don't want to get into that part. Okay, so here the pressure, temperature. So the pressure is a high pressure, very high pressure, and the temperature is very low. Okay, in that case, we could able to achieve a supercritical fluid. Okay, they like carbon dioxide supercritical fluid and carbon dioxide flow rate. These are the factors. These are independent variables. So extracting yield of bioactive compounds. So you just understand this one, central composite design. So D optimal design, I went actually for supercritical fluid extraction. When I talk about my PhD work, okay, that will maybe take some 40-45 minutes of video. Okay, we will after this closing of this unit 2, I will get into that part and briefly explain about my PhD work. And coming to the next part, box Benken design. When recurring fewer experiments than central composite design, as we told you in the last video, so it requires only a less number of experiments. So the advantage you know already, the cost reduction will be achieved. Okay, when avoiding the extreme condition that might be impractical. When avoiding extreme condition that might be impractical, in that case we can go for a box Benken method. When a quadratic model is needed but not required full factorial design, so in that case, but not requiring a full factorial design, in that case also we can go for a box Benken. So the example is a drug encapsulation efficiency in nanoparticles. The dependent variables is water. Efficiency of encapsulation is a dependent variable. Independent variables are polymer concentration, stirring speed, and solvent ratio. So our efficiency, the drug efficiency, okay, that is very important. That is a dependent variable that need to be maximized. Okay, in that case, we can go for a box Benken. So when a quadratic model is needed, then we can go for box Benken when compared to not requiring a full factorial design. When avoiding extreme condition that might be impractical, okay, in that case also we need to go for a box Benken. And requiring a fewer experiments, we can go for a box Benken. And the second example they have clearly stated here, light intensity, catalyst dose and pollutant concentration are dependent variables. Photolytic catalytic degradation is the response. Okay, so in that case we can go for a box Benken. So in a summary as a whole, when I need to go for a what do you call it, different types of design of experiments like a factorial design, RSM, Taguchi method, central composite design, box Benken design. Okay, so the multiple factors interaction important. In that case, we can go for a factorial design, non-linear relationship, process optimization, then go for a RSM. Taguchi method, variability reduction and quality improvement, then go for Taguchi method. Central composite design, quadratic model, second order effect. Okay, central composite design, reduce the number of experiments, box Benken, no extreme conditions. Okay, in that case, we can go for a box Benken method. So the example in terms of chemical engineering perspective which has been given for all the key points of design of methods, design of experiments method. This is called methodologies which we are talking about. And catalytic reaction optimization, polymerization, process improvement, we can go for factorial design. Biodiesel yield maximization, fermentation process efficiency, we can go for RSM. Injection molding of defect reduction, corrosion resistance, enhancement, we can go for Taguchi method. For central composite design, we can go for supercritical fluid extraction case as well as heavy metal absorption. The box Benken design, we can go for drug encapsulation in nanoparticles. That is the example. Photographic pollutant is not very, the examples are very limited. Only I just give an example when we need to go, but when we need to choose what is your objective, is that we need to see in the column of second column when to use this particular design of experiments. Hope you get an idea about design of experiments with a suitable example we see. And coming to the one example in a broader perspective, I just would like to highlight optimization of biodiesel production. So the dependent variables are methanol to oil ratio, reaction temperature and catalyst concentration. So this I named as methanol to oil ratio as x1, reaction temperature x2 variable and catalyst concentration x3. So if we see the yield, that is a dependent variable y is equal to x1 plus x2 some coefficients b0, b beta 1, beta 2. So when you see the x1 and the x2 are independent variables, x1, x2 and x3 are independent variables along with the coefficient of beta 1 and beta 2 and beta 3 respectively. The interaction between the variables x1, x2, x1 and x3, x2 and x3 are interaction that has been denoted with that has been along with the coefficient of beta 1 2, beta 1 3 and beta 2 3 respectively. Coming to the variables of x1 square, x2 square and x3 square, which talks about the quadratic effect, that is with the coefficient of beta 1 1, beta 2 2 and beta 3 3. This is a second order model with the quadratic equation. And coming to these variables, okay, what is a epsilon? That is an experimental error. So we, after doing this experiment, we also can find it out by using the obtaining this quadratic equation, the predicted value and actual value. That means by using this empirical equation, this empirical equation obtained from the experimental data. Non-empirical equation actually we used to have obtained from what you call theoretical basic principles, basic theories. Coming to the experimental results, so they vary the methanol ratio 4:1, 6:1, so 5:1. So they change the variable, the factor, by 3 levels, that is 4:1, 6:1, 5:1. So they didn't vary. Other than that, 3 factors have been taken here. You can clearly see from this table. The temperature, they have that is the independent variable. So what are the variable or what are the values they change? 50, 65, 57.5, 45. So between the variables, they have taken 45 to 65, 70. Okay, the minimum value is 45, maximum value is 70. And coming to the catalyst percentage, they vary from 0.5 to 0.25 to 0.75. So the system itself have arranged these factors, vary the different range, and they have taken. Okay, so biodiesel yield, which has been obtained by the experimental values, 82%. So it is very clear that 95% at the experiment number 9, ninth row, you obtain 95% of biodiesel yield, which states that this particular ratio, methanol to oil ratio 5:1, temperature 57.5 and catalyst percentage 0.5, we are getting the biodiesel yield is 95%. And analysis and optimization, quadratic terms, as I told you, x1 square, x2 square, x3 square, determine the curvature of the response surface. Interaction terms, x1, x2, x1, x3 and x2, x3, identify how variables interact. The optimal condition can be found by solving the second order equation using statistical tool, regression analysis, example, control plot and MATLAB and Python. Okay, so the MATLAB and Python, writing the code of solving the nonlinear equation with the quadratic effect, okay, we could be able to find the results of the variables. Okay, not only by RSM, we also can carry it out by MATLAB. And in RSM, we will get a contour plot as well as the 3-dimensional plot, the surfer plot can be obtained. So it will show the effect of the variables on 3 dimensions. Okay, 2 variables at a time, and then what is the effect on the third variable in a 3-dimensional plot can be obtained. Okay, so these are the things that the people will optimize the process. So what you need to take home is that the second order models capture curvature effect for nonlinear process, useful for process optimization in chemical reactions, distillations and material synthesis. Response surface methodology helps determine optimal operating conditions. So with this note, I would like to conclude this second unit. There is some additional classes is required on unit 1 as well as unit 2. That is a chemometric models for unit 1. I just would like to add on for the unit 1. And coming to the unit 2, I will just try to explain my PhD work as a additional out of syllabus thing, but for better understanding of the unit 2 regarding about the design of experiments particularly. So with this note, I just try to conclude my section today. We will continue with the next video shortly. Thank you for your time. Thanks for your attention.